In the last presentation, we began our exploration of combinational functional blocks, and we looked at value fixing, transferring, and inverting. In this presentation, we'll look at encoding and decoding. We'll start with decoding first. An n-bit binary code can represent up to 2 to the n distinct elements of coded information. Decoding is the conversion of an n-bit input code to an m-bit output code, with n less than m less than 2 to the n, such that each valid input code word produces a unique output code. There may be unused bit combinations here. Decoding is important since this function and the corresponding functional blocks are often incorporated into other functional blocks. Decoding is performed by a decoder, which is a combinational circuit with an m-bit binary code applied to its inputs and an m-bit binary code appearing as its outputs. We'll be working with n to m line decoders where m is less than 2 raised to n. Their purpose is to generate the 2 to the n minterms from the n input variables. Let's look at the simplest. That's a 1 to 2 decoder. On the left-hand side, we see the table for the function. Here, a is the input with outputs d0 and d1. If a is equal to 0, then d0 is equal to 1 and d1 is equal to 0. If a is 1, then d0 is 0 and d1 is 1. So d0 is equal to a naught and d1 is equal to a, which allows us to design the very simple circuit to the right. Let's see how we can extend this to a 2 to 4 decoder. Here we see the truth table for the 2 to 4 line decoder. The table has 2 variable minterms as its outputs, with each row containing 1 output value equal to 1 and 3 output values equal to 0. Output d sub I is equal to 1 whenever the 2 input values a1 and a0 are equal to the binary code for I. There are 4 possible minterms, so we're going to need 4 outputs. This is an implementation animation of the 2 to 4 line decoder circuit in CircuitVerse. You can also see this on page 129 of the text, except there's a slight error in the labeling of the diagram there. If you look closely, you can see the AND gates are connected to 2 1 to 2 line decoders. Large decoders can be constructed simply by implementing each minterm function using a single AND gate with more inputs. Unfortunately, we end up with high gate input costs. Instead, we can use a hierarchical approach. To construct a 3 to 8 line decoder, that's n equal 3, we can use a 2 to 4 line decoder and a 1 to 2 line decoder feeding 8 2 input AND gates to form the minterms. Hierarchically, the 2 to 4 line decoder can be implemented using 2 1 to 2 line decoders feeding 4 2 input AND gates. Let's look at the general procedure. You can find a description of the general procedure for constructing decoders using hierarchical approach on page 129. The authors show how you can use this procedure to construct a 6 to 64 line decoder, which is pictured here, with the gate input cost of 182 versus 390 for the completely naive approach. When using this approach, it's good to note that the alternative expansions are possible. The example also allows some choice in implementation. There is a formal implementation of the algorithm, but it's beyond the scope of the text. We can implement the function n to m line decoding with enabling by attaching m enabling circuits to the decoder outputs. Then m copies of the enabling signal en are attached to the enable controls of the enabling circuits, as we can see here. The circuit you see here in this figure is referred to as the decoder demultiplexer. Here, information received from a single line is transmitted to one of 2 to the n possible output lines. The 2 to 4 line decoder with enable in this figure is an implementation of a 1 to 4 demultiplexer. We'll get to the multiplexer later in this module. The decoder provides the 2n minterms of n input variables. Since any Boolean function can be expressed as a sum of minterms, one can use a decoder to generate the minterms and combine them with an external OR gate to form a sum of minterms implementation. The procedure for implementing a combinational circuit by means of a decoder and OR gates requires that the Boolean functions be expressed as a sum of minterms. We can get this from the truth table or by plotting each function on a K-map. We then choose or design a decoder that generates all minterms of the input variables. The inputs to each OR gate are selected as the appropriate minterm outputs according to the list of minterms of each function. Let's see how this works with a 1-bit binary adder. This is a decoder and OR gate implementation of a 1-bit binary adder. Here the minterms for S are 1, 2, 4, and 7, and the minterms for the carry or C are 3, 5, 6, and 7. Since there are 3 inputs and a total of 8 minterms, we need a 3 to 8 line decoder along with 2 OR gates. We'll see addition as a topic a bit later on in this module. The decoder method can be used to implement any combinational circuit. However, this implementation must be compared with other possible implementations in order to determine the best solution. An encoder is a digital function that performs the inverse operation of a decoder. An encoder has 2 raised to the n input lines and n output lines. The output lines generate the binary code corresponding to the input value. Let's take a look at an example. Here we see the truth table for the octal to binary encoder. This encoder has 8 inputs, 1 for each of the octal digits, and 3 outputs that generate the corresponding binary number. It's assumed that only one input has a value of 1 at a given time, so the table only has 8 rows. If we wanted to make it bulletproof, we'd need 56 more rows and a bunch of don't care conditions. In figuring out our octal to binary encoder, A0 is 1 for D1, D3, D5, and D7. A1 is 1 for D2, D3, D6, and D7. A2 is 1 for D4, D5, D6, and D7. And so we can implement this directly with 3 4-input OR gates. This is pretty cool, but it's got some drawbacks. The encoder just defined has the limitation that only one input can be active at any given time. If 2 inputs are active simultaneously, the output produces an incorrect combination. For example, if D3 and D6 are simultaneously 1, the output of the encoder will be 111, because all 3 outputs are equal to 1. This is neither a binary 3 nor a binary 6. To resolve this, we need to establish an input priority so that only one input is encoded. We establish a higher priority for inputs with higher subscripts. Another ambiguity in the octal to binary encoder is that an output of all zeros is generated when all the inputs are 0, but this output is the same as when D0 is equal to 1. We can resolve this by providing a separate output to indicate that at least one input is equal to 1. A priority encoder is a combinational circuit that implements a priority function. The operation of priority encoders such that if 2 or more inputs are equal to 1 at the same time, the input having the highest priority takes precedence. V indicates valid output. The table for a 4-input priority encoder is shown here. X's in the output column correspond to don't care conditions, while X's in the input column are used to represent product terms that are not min terms. You may have noticed that the table in the last slide was missing some rows. For example, 1XX actually represents 8 different rows. You can use either a condensed version of the table or make the full version. In the next step, we get the min terms for A0 and A1 and simplify them using K-maps. V is the OR function for all the input variables to indicate valid output. We can now implement our priority encoder using the results from the K-maps. Encoders can expand to larger numbers of inputs by expanding OR gates. Designing multiple level circuits with shared gates reduces the cost of the encoders after technology mapping. Thanks for watching. I'll be back soon with a discussion on multiplexers.